Hello everyone. Today let's see about wireless communication. The subject code is EC3501. The third unit is modulation techniques, equalization and diversity. Let's see the first topic, that is digital modulation and overview factors that influence the choice of digital modulation. These are the topics in third unit. Let's start with the first topic, that is digital modulation. Let's see about the modulation techniques. We know modulation is the process of encoding information from a message source in a manner suitable for transmission. Modulation may be done by varying amplitude, phase or frequency of a high frequency carrier in accordance with the amplitude of the message signal. These are the block diagrams of modulation and demodulation techniques. For modulation, there are two inputs. One is modulating baseband signal and high frequency carrier. Output is the modulated bandpass signal. And demodulation is the reverse process of modulation, that is extracting the baseband message signal from the carrier. Here the input is the bandpass signal plus noise that is present in the channel. So the output of the demodulation is baseband signal. Let's see the types of modulation. There are two types of modulation. One is analog modulation and digital modulation. The basic types of analog modulation includes amplitude modulation, frequency modulation and phase modulation. There are several types in digital modulation. Let's see that one by one later. So in the case of analog modulation, the first one is amplitude modulation. Amplitude modulation is a process by which the message signal is transmitted by varying the amplitude of the carrier wave in accordance with the amplitude of modulating signal. So if you see the waveform, the first one is the message signal, second one is the carrier signal, and the third wave is the amplitude modulated signal. Second one is frequency modulation. Frequency modulation is a process of encoding information by varying the frequency of the carrier wave in accordance with the amplitude of the modulating signal. Here in the waveform, the first one is the message signal, second one is the carrier signal, and third is the frequency modulated signal. The third type of modulation is phase modulation. It is the process of varying the phase of the carrier wave in accordance with the amplitude of the modulating signal. Here the third wave is the phase modulated signal. Now let's see about the digital modulation. Digital modulation is the process of encoding a digital information signal into the amplitude, phase or frequency of the transmitted signal. Here we have three types. The first one is amplitude shift keying, second one is frequency shift keying, and third is the phase shift keying signal. Let's see that one by one. So the first method is the amplitude shift keying, ASK. It is a form of amplitude modulation that represents digital data as variations in the amplitude of the carrier wave. So see the waveform. Here the first one is carrier wave, second one is the digital data, that is the modulating signal, and the third one is the ASK signal, that is amplitude shift keying signal. Let's see about frequency shift keying. It is a digital modulation technique in which the frequency of the carrier wave varies according to the digital signal changes. Here the first signal is the digital data. It is in zeros and ones. And second one is the carrier. Second one is the high frequency carrier, and the third signal is the low frequency carrier. And the last wave, it is the FSK signal, that is frequency modulated signal. And next let's see the phase shift keying. It is a digital modulation technique in which the phase of the carrier signal is changed by varying the sine and cosine inputs at the particular time. Here the last signal is the last wave is the phase shift keying signal. So now let's see the overview of digital modulation. Modern mobile communication systems use digital modulation techniques. Digital modulation is cost effective when compared to analog transmission system due to advancements in VLSI and DSP. We know that VLSI is nothing but very large scale integration and DSP is digital signal processing. Let's see the advantages of digital modulation over analog modulation. We know that digital modulation is greater noise immunity. It has greater noise immunity. It is robustness to channel impairments and multiplexing of various forms of informations such as voice, data and video is easy in the case of digital modulation and security is more in the case of digital modulation, and it can also accommodate digital error control codes, and it also supports complex signal conditioning and processing techniques such as source coding, encryption techniques and equalization techniques. These are the advantages of digital modulation over analog modulation. So, now let's see the factors that influence the choice of modulation. A desired modulation scheme must provide low bit error rate at low signal to noise ratio. This is represented in terms of power efficiency and energy efficiency. In addition to this, a desired modulation scheme must perform well in multipath and fading conditions. It must occupy minimum R of channel bandwidth, which is represented by bandwidth efficiency. It must also be cost effective and easy to implement. So, depending on the demands of a particular system or application, trade-offs are made when selecting a digital modulation scheme. Now, let's see the factors that affect the choice of digital modulation. There are three factors. One is power efficiency, second one is energy efficiency, and next we have the bandwidth efficiency. So, the power efficiency, it describes the ability of the modulation technique to preserve fidelity of the message at low power levels. It is usually in order to obtain good fidelity, the signal power needs to be increased. But there is trade-off between fidelity and signal power. So power efficiency, this factor describes how efficient this trade-off is made. Power efficiency is denoted by eta P. It is nothing but the ratio of EB to N0. That is, EB is signal energy per bit and N0 is noise power spectral density. And second factor is bandwidth efficiency. It describes the ability of a modulation scheme to accommodate data within a limited bandwidth. It also reflects how efficiently the allocated bandwidth is utilized. So bandwidth efficiency of the modulation is another factor. It is denoted by eta B. It is the ratio of data rate to bandwidth. Data rate is denoted by R and bandwidth is denoted by B. And data rate is represented in terms of bits per second and bandwidth is represented in terms of hertz. So a fundamental upper bound on achievable bandwidth efficiency is given by Shannon's channel coding theorem. Shannon's channel coding theorem states that for a small probability of error, the maximum possible bandwidth efficiency is limited by the noise in the channel. This is the expression for Shannon's channel coding theorem. It is the ratio of channel capacity to R of bandwidth. It is nothing but log 1 plus SNR to the base 2. SNR is nothing but signal to noise ratio, that is the ratio of signal power to noise power. Here in this expression, C is the channel capacity, B is the R of channel bandwidth and S by N is the signal to noise ratio. So this is taken from the textbook Wireless Communication by Rappaport. Thank you.